Hey everybody, this is Mr. Reynolds here, and yeah, I decided to travel to the beautiful island of Miyajima. This is found off of the coast of Hiroshima. You see the beautiful floating torii just right down there. The tide is out, which is why it's not really floating right now, but beautiful island. If you ever get a chance to get down there, I would highly suggest it. I wanted to do a little bit of introduction for what we're going to be doing the next 2 weeks because I think a little context may help you sort of understand what's going on. We're going to be shifting to particle physics. Now, particle physics is talking about all the tiny little particles that make things up, make up our universe. For many years, people thought that there were just a few particles that made up everything. For chemistry, you might have heard that there's things like the proton and the neutron. Of course, the neutron has a neutral face, and then the electron. And every single atom could be made up with some combinations of protons, neutrons, and electrons. And all the experiments we did led us to believe that that's all there is. But then we kept doing more experiments. Then we kept testing more things. We kept improving our equipment, trying some new things. We found out some weird stuff. It turns out that these maybe aren't the only particles. In fact, one thing we found is there's some evil mirror universe evil clones of these. So while you have for example, you have a proton here, you also have an antiproton. Ooh, see how they're totally opposite from each other? Mirror universe. It's antiproton. These come in contact, big explosion. Same thing with neutrons. We have a neutron and there it is, antineutron, okay? Don't want those to come in contact. We talked about these two before. We have our electron and our positron. Now, they're both happy because they're particle physics buddies, but notice how all the colors are opposite and everything like that. These are antiparticles. Okay, so we started seeing these antiparticles. Then what we did is we started taking protons. Here are our protons. And we started smashing protons into each other. We started smashing them into each other, and we saw that things came out. Now, if the proton was just the most fundamental simple particle there could be, and I hit them together, they would just have to bounce off. Because if you were the most fundamental simple particle, even though you can apparently disappear magically, then how would you break apart if you were as simple as can be? And it turns out that this isn't as simple as it can be, that the proton is made up of other things. The proton, neutron, electron are not the only things in the universe. In fact, the proton is two of these, two up quarks and a down quark. Two up quarks, I only have one of them, so you only see one. Two up quarks and a down quark. And so when you put those together, you're going to form a proton. That's what a proton is. It's two up quarks and a down quark. Why do we call them up and down? Well, what do you want to call them? You know? They're so small, we can't really describe them. We can only recognize them from experiments. So we have the up and down quarks. They're the easy ones to find. Then we start hitting things together with more energy and more energy and more energy. We found weird stuff. Maybe we found things like the strange quark. Look how strange it is. It's got 3 eyes. All these quarks also have antiparticles. Here's the anti-strange quark. Ooh. And all these quarks existed, and they're all in different combinations. And these quarks, what they really allowed us to do is they allowed us to complete the equation. With more and more observations we've made, we had more and more questions. The model we had for the universe just didn't fit anymore. And so what we've done is we've developed this model of all these different things that are out there. We can't see them. They're way too small to see. But they're ideas we come up with. And we say, well, okay, so let's say there's a quark, has these properties, does these things. This is what should happen. And if that thing happens, then that gives us more evidence that, okay, maybe we're right about this up quark. Put all together, we're gonna talk about all these different little parts of what's called the standard model, including things like quarks and leptons. We have things like these are bosons. This is a photon. A photon does a neat thing. So if I have two positive charges right next to each other, what are they going to do to each other? Right, they're going to repel. But why? And are they immediately going to repel? If I just put a positive charge there, will the other charge immediately fly away? Well, maybe not, because nothing travels faster than the speed of light. No information travels faster than the speed of light. Us going around the sun, the Earth is being pulled around the sun by gravity. If the sun and all of its mass just disappeared, would the Earth know about it? Well, it would know about it eventually, but it would take about 8 minutes. That's about how long it would take the graviton, the force carrier, the boson that brings the force, that mediates the gravitational force to us. It would take that long for the Earth to know, hey, the sun's not there anymore. You go in a straight line. When you put your hand up against a table or something like that, it's the electrical force that's pushing your hand away from the table. That's what's keeping your hand from pushing through the table. In order for your hand to know the table is there, your hand is giving off photons. The table is giving off photons. They're interacting with each other, interacting with you, and they are transmitting that electrical force. We even have things for the strong and weak nuclear forces, the Z boson, the W plus, W minus boson, and the gluon. So we're going to be talking about what we know right now to be the most fundamental particles. Now, through this whole discussion of particle physics, at no time do I want you to think that we have it all figured out. We don't. I'm going to show you what the current model is. I'm going to show you what we know of right now. We're discovering new stuff every day. I know you probably remember a few years ago, we got enough evidence to say that we discovered this. This is the Higgs boson. We are currently trying to build bigger colliders to discover bigger things. More energy is going to let us see more stuff. So I'm going to have you watch this video by CERN. Talks a little bit about it. And then this first lesson is going to be just sort of introducing you to some of the different categories. What are some of the different categories of particles? We have 3 main categories, and then they can combine to do a few different things. The second lesson for the week is going to be looking at the individual particles, the up, down, top, bottom, charm, strange, the electron, muon, and tau, and then the neutrinos that go with that, and all the bosons. Next week, we're going to talk about how they relate together. We're going to talk about how they interact together. We'll look at beta decay. We're going to look at beta decay from a particle physics level to understand what's happening and why. We're going to be drawing Feynman diagrams. Guys, this stuff is pretty interesting because this is the knife edge tip of where science is right now. If you go to be a physicist down the road, you might be adding to this model. Teachers in a few years might be teaching something different because of what you discovered right here with this content right here. Okay, so watch this CERN video, and then we'll be back with a little iPad video just sort of talking about some of the different particles and what's going on with that, and we'll call it a day there. Hope you all having a good day. Hope you all safe, and good to see you, even though I'm not really seeing you. Whatever. Farewell from Japan.